Good morning, afternoon, evening, or night, ladies and gentlemen, depending on where in the world you're located, or indeed, good yesterday for those quantum structural engineers out there who are the fourth really at the forefront of our technology. My name is Duncan Hendy. I am product marketing manager here at IDEA StatiCa. I'm very excited to introduce this webinar and also my co-hosts who are Andre Hudetz and Adam Kojoshek. So how are you guys doing today? You're excited about this presentation?
Thank you, Duncan. I'm doing great. Very excited. Good morning, all ladies and gentlemen.
I am. Good day to everybody. I am overexcited as always, and bon appetit to everybody who's having a lunch right now.
Okay. So as you can see, we're all very excited here, and we're really struggling to contain it because it's Connection Wednesday, but this time it's with a twist, and we don't mean the popular 1960s dance, or do we? Oh, so before we proceed, we'll go through a little bit of webinar what we call etiquette. First of all, you'll find that all your microphones are muted by default, but do not fear. There'll be plenty of chances for you to interact with the webinar as we go through. You can submit your questions. As you can see on the slide, there's an indication of how you do that. Please do submit your questions throughout the webinar. We will address those at the end of the webinar. We also have some polls that you can take part in during the webinar as well. So without further ado, let's have a look at the agenda. So the introduction, well, you probably guess that's what we're doing right now. So we're going through it, and then we will be following up with an overview of the Twist project, which is carried out by the Ramboll Group in Norway, which shows you that no matter how groundbreaking the project is, with the right tools and resources, the sky's the limit when it comes to form and functionality. And Adam will show you some of the twisted and beautifully sophisticated ideas behind the museum. And then will come the first practical demonstration of the webinar, where Adam will walk you through how to model your very own frame joint with tubular members, like in the project using IDEA StatiCa Connection. And then Andre will then twist the webinar in his direction and show you the BIM links workflow from the project using both FEA and CAD data. So at the end, as my mother always used to tell me on wintry days like these, we will wrap up well at the end. So before we start, we're going to go to the first poll of the webinar. So I will launch the poll. Please do participate in the poll. We really want to know how often you attend these kind of
So how often do you guys?
Well, every Wednesday. There's a Connection Wednesday. I'm there.
That's good. Every Connection Wednesday I attend as well.
I think you're kind of obliged to do that.
Kind of, yes.
Okay. So, oh, we have a few newbies. That's quite exciting. First timers, hopefully not last timers.
Yes, I see 80% of our attendees already voted. That's good. Yep. And it's rising, so yes, we can finish the poll. Yes.
Wrap it up. So, yeah, so sometimes maybe a few webinars a year is the most popular one. Okay, great. So
I'll share the results with our attendees as well.
Mm-hmm.
Okay, nice. So we have some regular visitors and sometimes visitors and even some first-time visitors. So welcome to our shows. Good. So I'll hide the results now, and I will take the presenter. Is that right? Would you let me, Duncan, to do that?
I certainly. Shall I let you do that? Yeah.
Thank you. Okay, so I'll share my screen right now, and that brings me once again, and I'll share the right screen, which is this one. Okay, and there you go. So I'll continue with the presentation of the project, which is the Twist Museum. And at this slide, I would like to thank a lot to Rambo Group, our good customer that we have for almost 10 years on board, that provided us with this presentation that celebrates the work and this project overall. So with big thanks, I will just say it in my words. So this is about the Twist Museum in Kistefos. Sorry. Kistefos is a place in Norway to the north of Oslo, the capital. And it is a natural beauty sculpture park and a museum at once. So we know the location, and the investor here was indeed the museum itself. And we'll take a look at the architectural design of the Twist, since we know where it is and who is behind it. The main architect was the big, that means Bjarke Ingels Group, this architectural design office. This is a Danish company that grew up to become pretty much an international company with multiple offices around the world. And they do those very artistic pieces of architecture, these special buildings and structures that really amaze people and are put in special places. So they took over the project and the preliminary design. The idea why to build this structure, which is actually a bridge, was that this sculpture park is located in the river valley, a beautiful natural place. And basically the museum wanted to connect these two loops into one, so that the visitors of the place would go in one circle around to visit all the museum locations and galleries. So that was the motivation how to build a bridge. And at the same time, they said themselves, okay, why just having a bridge? Let's make something special and put a gallery on the bridge at the same time. So very smart idea. Now, when we come to the terrain and the location itself, and the idea behind the twist. So it is so that in one bank of the river is very shallow and flat, and the other bank is quite steep. And so that's why actually this solution to twist the bridge, that is where it came from. And at the same time, it brings a bigger value to the gallery space itself, that you have, let's say, 3 segments here. One is rather tall, so you can install these rather total pictures and sculptures and objects. Then you have the twist part, which is indeed a very special place to go through and observe installations there. And then you have the, let's say, standard flat space for other installations. So this marvelous idea brought a technical solution on one hand and a added value to the gallery space in the second hand. Right, so this is the mechanism of how the structure was designed by the architect. So simply take a steel structure and twist it in between. So simple as it is, but at the same time, quite a challenge for the structure engineers, right? And the designer of the steel construction. So let's see how they dealt with that. So this was carried out by Ramboll Group, as I said, also sitting in Denmark at the time. So that's a pretty much international project already. So Ramboll engineers, about 10 years ago or 8 years ago, when they were dealing with this project and making it done, already used a couple of advanced softwares in cooperation with the architectural office. They used the parametric approach in Rhino and Grasshopper software tools. So that's how they designed and optimized the shape of the structure itself. And then the designers use TECLA for the CAD model and drawings, and robot analysis tool for the global analysis of the steel structure, right? So this is the software tool package that was in their hands that time, 8 years ago. So this is a scheme of the Grasshopper. Those who work with Grasshopper or in parametrics are familiar with that. And that basically allows you to operate and manipulate the BIM model that is produced from Rhino. And as you can see on the picture, that's the final shape with these 3 segments highlighted. All right, when it comes to structural calculations, as I said, the static and dynamic analysis was done in Robot from Autodesk, the global analysis. And of course, here's our well, place of fame, that for the connections, they used IDEA StatiCa Connection. That used to be version 7 and then 8. So pretty much an old version, but at the time it was perfectly helpful and helped Ramboll engineers to carry out the structural design of steel connections of this structure. What is interesting that at that time we were about developing the first BIM links. The first one went out with TECLA structures, and they even took advantage of that. Was still limited, so not all the connections came from TECLA to IDEA directly, but some yes. For Robot, the BIM link was not yet developed, so for bringing into connection models the internal forces, the load effects, they used the Excel import instead of a BIM link. But that was about 8 years ago, and today the whole process and workflow is pretty much well tuned and very well working. And my colleague Ondra will show you that after my part. So there is something to look forward to. And you also see some of the examples of the connections that are pretty complex. They are pretty spatial 3D connections. So hard stuff to deal with. Even some of the connections are very, very simple and standard, but also Ramboll engineers took advantage of IDEA StatiCa to use it to design sorry, and code check those. All right, enough of that. Then the last step was, after they tuned the structural design and the connections, they sketched everything and put together in Tekla, produced the Tekla CAD model, and carried out the drawings. Then it went out to construction. So this started in Poland. So another country involved, another company involved. In Polish workshop, they basically built a multiple segments of this bridge gallery. Then they shipped it to Norway, to the location of Kistefos, and there the construction on the temporary bridge over the river started. So we have a couple of pictures. This is for steel connection lovers. And the Remy picture, this is the middle part, the twist. You can see this is a pretty complex piece. An overview of the structure under construction. The construction is finished, and now the cladding started. One more view from inside, and the facade started to be installed, and the cladding inside as well. And we can see now the finished building or the bridge in place. And this is really a piece of art. I personally really love these screenshots, that you have a amazing structure and this beautiful landscape over the river that serves its purpose. One more view from inside. That's a place you want to visit, right? At least I do. Okay, so by this I would conclude the presentation of the project. Hope you got it excited. And I'll jump into the practical part of this workshop, or the first practical part, and that will be a modeling of one of the connections from this structure. And it is such a connection. So I will do this step by step to show you how to create this design, and I will point out a couple of tips from my side for your modeling practice in IDEA StatiCa Connection. So I'll jump into the connection app, and I will start a new project. So this is the new project screen. So I'll just go for some starting template, whatever, for example, this one, and create a new project. Good. So this is my design tab, and here I will perform the creation of the model itself. So first I will delete those operations from this starting template, and I will modify the geometry of these two members, the column and the beam, sorry, to form the frame corner. So the cross section of this column and the beam is HEM, so it's an I section, and I change it here. Here I see the list. Sorry, my graphics of sharing on GoToWebinar somehow corrupted, but anyways, there's a list of the vast library of cross sections produced standardly, and instead of navigating through it manually, I can take advantage of this search here, and I just type in the cross section I would like to have and select it. Push enter or OK, And there we go. So that was my first tip, the search in the library of cross sections. For the second member, I just choose the already edit cross section and change the pitch of it to 0 degrees. All right, basic geometry done. Now I will weld these two members together. So I will start adding the manufacturing operations, and first I want to make the beam longer so it ends with the left face of the column. So I use cut operation for that, and here I select member B cut by member C, that's right, and I want to extend the member to its farther face. So cutting plates not closer, but the farther place. All right, there we go. And I'll add some offset, sorry, for the weld that I will add in the next step. And I will add the welds by adding another cut operation. And at this time, I'm cutting the column C by the member B. You see, it's done automatically, and the only thing I want to do is to change the size of the welds to 20 millimeters. Okay. Then I'll add stiffeners to form the frame corner. So another operation, stiffener. And here I just set the member B, which is, and the stiffeners are related to member C. By this, I automatically get the result I want to have. That means the thickness of those stiffeners is aligned with the stiffness of the flanges of the column. It's welded all around. Both stiffeners are installed at the same time on both sides of the member B. So that's correct. I'll just change the weld thickness to 20 millimeters and chamfer the corners inside to make space for the curved rolled section between the web and flange. And this chamfer will be 40 millimeters. Good, frame corner is done. And now I will add those, I'll show you where we are. I will add now these two tubes welded to the member web. So I will add a new member and change its cross section to the CHS, so a tube. So I'll select this one, and here go back. Oops, this is a unpleasant display obstacle, but no worries. I want to input a CHS, so I typed it in. It's 323.9 of diameter, and now the thickness is 45. So that's not in the library because it's over the standards produced. The maximum is 25 of thickness, but no worries, I can solve this easily by choosing a custom tube or general tube as a cross section and simply type in the values, and there we are. The member is formed, and I will put it in the correct location. So for that, I need to know the vector or the angles of the member, which is minus 93 degrees in horizontal and minus 22 in vertical. So you see from the top view that the tube is not perpendicular, but it's a spatial structure, as we saw from the pictures of the twisted part of the bridge. All right, and now here we come to another tip or trick from my side to show you, and that is, now we have two options, right? So either we design this tube to be continuous and go through the member web, or we form two tubes welded to the web. So I'll show you first the continuous tube. So I switch here from ended to continuous member. And now to cut it through and weld it at the same time, I use the operation cut. Okay. I select the tube. I select the member B. Oh, sorry, it's vice versa. I select the B because this is going to be cut by the tube. And the trick here is to switch from bounding box to surface. And that already creates a cut in the web. You see this is hollow now. And I see the weld on this side, but it's missing on the other side. I can easily fix that by changing the weld settings. So there are no flanges on the tube, only one web. And I switch to double fillet weld and make the weld bigger. So you can see I have a nice round weld on both sides of the tube. Okay, so this is one option. And then I'll show you the second one that was used in this project. And so that I will delete this and I'll go back to the ended type of the tube. And I will copy this member and add it to the other side as well. So for that, I need to change the vectors here. These angles you need to read from your structure model or from a CAD model. Or in case you use the BIM links that you will see in a couple of minutes, you don't need to input this because you will have all the data imported. But anyways, how to deal with this now? I want to weld these tubes to the member web. So I will use again the cut operation. But first I need to extend this tube. As you can see, it ends here, just a couple of centimeters front of the web. So let's extend this member by member B. Again, I'll push extend the member farther, and you see it goes through here. So now I will use another cut operation to weld it. So this tube, member B, again, it's cut and welded at the same time. I switch off the flanges because there is no flange on the tube. Change this to 20 millimeters weld size, and you can see a very similar thing as I showed you 2 minutes ago, but there is no hole in the member web. And that's the way I wanna have this constructed. So for the other side, I will use a trick of multi-select, which is my another tip from my pocket. So I select both operations at the same time. I copy them, and those copied I select as well. And here I switch the member from M5 to M4, and you can see this is applied at once. So I saved at least 1 minute by this, and I can continue modeling the last part of this connection. I'll bring here the picture again, and that is this diagonal member connected by this connecting plate and a gusset plate. Okay, so I will add the diagonal member. There, I need to change the cross section. It's not the same as the main structural tubes, but it's thinner. So in this case, it's 305 and thickness is 16 millimeters. And of course, the vector or the orientation of the member is also different, and it goes like this, 67 degrees in this rotation and minus 8.6 in vertical. Okay, so a real 3D connection. Now, how to connect this? I will use the connecting plate operation, add it to my operations list. And from the parameters displayed now on the right side panel, you can see this is a pretty complex operation with a lot of options. But don't worry, I'll show you around and I'll show you how to apply it. So first thing is that I will select the member I want to apply the operation on, obviously the last member. And this will be related to this tubular member to which the gusset plate will be welded. And you can see already some gusset plate here formed. You can see a cap plate, a thong here. And now my task is to modify this to the desired shape. So first thing I will do is I will shift the face of the tube to 1200 millimeters. So that is the distance between, you see, the face of the tube and the node or the connection center, which is here where all the members meet. All right, that was the first thing I did. Now I will change the type of this connection between the tube and the plate from a cap plate to a notched member that looks like this, a plate that cuts through the tube. If I go to transparent view and you can see the cut here in the tube on both sides. Now, if you would like to do it a different way, that you want to rather cut the plate instead of the tube, there is this other option, notched plate walls. So if I do that, you can see the cut changed and now the plate is cut. Right. So that was another tip from my side. And I'll go back to notch member and the solid view, and I will form this this thong of the connecting operation. So first I need to define the length and the width. So the length is 230. That's the dimension from the tube end to the end of the plate. You can see it here. And the overlap, that means what goes inside the tube, is 350. Okay. Now the width, 360. There we go. Anytime you can use the measuring tool, which is sitting here in the 3D window, and measure what you have created. You can pick, for example, these 2 points and see the dimension of the width of the plate. Now the measuring tool, that's a new feature since the latest version of IDEA StatiCa, and it's very useful. But let's go back to this plate. So I'll change the thickness here to 40 millimeters. And I will also define the welds here. There are some edit only outside, as you can see, not inside the tube. That's correct. And that's this weld on the tongue. So I'll change its size to 8 millimeters. All right. So that's this. Now I will move to model the gusset plate. Its parameters are located here. And here what I'll do is also change the thickness to 40 and make it much bigger. So 1000 millimeters of length or width, and the depth of 460. Okay, so now we have a big plate that extends through the beam. So I will shift it a bit so I have it in the right position. Okay, and now I need to shape it, of course. So first thing I do, as you can see now, the plate is lying on top of the tongue. So that's one type of a connection I can produce. But in this case, I want to produce a connection with splices on both sides. So I need to align these two plates in one plane. So how do I do that? It's here, alignment, parameter, front or rear, that's the other side, obviously. And the center is what I want. So you can see now the plates are in one plane. That's good. Now I can change the weld here. That was formed automatically as well. That is the plate weld. Sorry. So I change the thickness to 8 millimeters. Good. And of course, I want to shape this plate now. So shaping the plate is possible to do in two ways. First way is right click on the plate and open the editor from here. That goes like this. The same approach is here, that I open the editor from the parameters tab. Here I can add various operations to change the shape of the plate. So for example, I can go like this. Add a bevel, add it to the point, and just change these values to obtain the desired shape. Okay, so that's one way. It is advantageous in certain situations where you wanna shape the plate manually this way. You can also see the drawing of the produced plate here. But there is another way which is more practical in this example. So I delete this shaping operation from the editor. I will skip the editor and I will rather shape the plate using manufacturing operations. And that is first the working working plane that will serve as a cutting plane in this case. And I will set this work plane on the diagonal member so I can work with it more easily, placing it in the right position. So I choose the origin on the member, choose the diagonal member, and you can see now the working plane is placed in the node of the connection where all members intersect, and it's these 1200 millimeters that I inputted previously here, shifted, right? So that's the distance now. So if I put it here in the X distance, now I have it on the face of the tube, but I want to have it right here to in order to cut this plate and leave some gap between these two plates. So I can measure these dimensions, for example, from this surface or edge to this edge. This 230 plus 20 millimeters gap here, that's 250. 1200 minus 250 is 950. All right, that's how I work with the working plane and the measuring tool to get it all done. And now, since I have the working plane in the position, I add a cut operation, and I will select here, sorry, I was wrong operation, not cut off member, but cut off plate, this one, because I'm cutting a plate in this case, not a member. So my plate is this one. It's named as CPL1A. It's part of this connecting plate operation, and it will be cut by a working plane, which is selected automatically. And now I see that it cut it the other way I wish, but simply change it here. So instead of cutting the one side, cut the negative side. Good. First edge is cut from my plate. Now I do the same with the other side. So I copy these operations again using the multi-select. And for this working plane, I change the position. So I go back to 0. I rotate it. Okay. And now I input the distance to shift it, to align it with this edge, which I measure and calculate as 154. Good. Now just switch here from working plane 1 to number 2. That was added in the previous step, and there we go. The plate is shaped. One last thing here I need to do around this plate is that the program is informing is that there is a plate clash, that this plate goes through the member B, as we can see here a little bit. So I need to cut it here as well and weld it to the web. So I use this cut-off plate. I can copy it again, and instead of cutting plane, I am cutting by member, which is member B. And the cutting method is not bounding box, which is around the eye section, but rather the surface which finds the surface of the web. And again, I switch to the positive part of the plate. The weld is added as well, so I modify to double fillet weld and change the thickness to 8 millimeters, so we can see it here. All right, so this is formed, and the last thing is those splices here and bolts. So how to add these two splices? I will use a general plate operation, which we call the stiffening plate. And form it here. So I will place this plate on top of the existing plate, this one. Okay, so I select it. And here I will say I don't want a rip that looks like this, but I want a, doubler. A doubler looks like this. It adds a plate that's lying on another plate. I will switch it to the other side. And now I will change its size so it matches with the plate underneath. So the height on one and other side is 180. I turn off the welds here because the plates will be bolted. I change the thickness of this plate to 20 millimeters. I shorten the plate on the lower end and make it longer on the other end. The overall length is 440 millimeters, and I will move the plate a little bit from the tube face by 20 millimeters, like this. Now you can see I added -20 because the plate local coordinate system is aligned with the member coordinate system, and the x-axis goes into positive towards the free end, right? But I want to shift the plate the other side towards the node, so that's why I inputted -20. All right, but I have the plate in place. This is what I like. How to put it on the other side? Just copy this one and switch to the front. Good. Now the splice is prepared and we need to bolt it. So I will go to operations and at the operation fastener grid or contacts. This operation allows you not only to form bolts, but as you will see, there's a drop-down menu that allows you to use pins, anchors, and contacts, any shape, position, or place you like. But this time I'll go for bolts, obviously, and I'm connecting 3 plates. So here items is number 3, and I select the plates that should be connected. This one, and this one. So 3 of them highlighted. Now my bolt size should be M36, which is, again, I have this display error, a nasty surprise from GoToSharing, but anyways, we can go through that. The size is changed, and now I need to place the bolt grid. So by changing these rows and positions, there are some tooltips how to work with those 2 parameters. What I do is that I put the bolt in 0 position. That means the beginning of this plate here and the center of the plate here. So first I will create the 3 rows. So 1 row is in middle of the plate, second row is 120 millimeters to the left and 120 millimeters to the right. Good, 3 rows of bolts produced. And now to shift it is being done by this position parameter. So first is 50 millimeters, again minus because we are going against the x-axis. I see that I mentioned here. And from this first row of bolts, I want to generate a second one, which is 110 millimeters. Again, I have to go with minus. So I have 2 rows of bolts. That's good. And now I copy it and I will just switch here the middle plate to this one. That's good. And I will form or switch the positions. So again here I will go to 0 to show you the logics. Now the distance between the beginning and the end of the plate is 440. So if I go minus 440, I will have my bolts on this edge. And from here, I want to go by 50 millimeters towards the free end. So plus 50 is minus 390. Okay. And from here, I want to add one more row, 110 millimeters next to it. So this is the logic behind positioning bolts and some practical ways how to quickly achieve what I need. And that brought me to the end of our modeling of this connection. We are finished. So you can see the whole connection model. The last step now is to add the load effects and let this connection calculate it and code check. So one load effect was automatically generated with my starting template, but of course I don't want to use that. Instead, I want to import forces from XLS. That means an Excel sheet. So that is this function here. So I will bring my Excel tab that is here. My Excel tab is an export of internal forces calculated in the global structure model. In this case, it was the robot software that calculated the whole structure. And what I will do is select all these about 50 load combinations and their internal forces at once. I will copy them and paste them into this tab in IDEA Connection. Now the data are being transferred and you can see all of them here. So I will replace the existing one combinations. By this, I will delete this LE1, which I want, and I will only add the 50 load combinations from my Excel sheet. I can see them here. You can see these numbers. So that's pretty useful not to input all those numbers by hand, right? That would be a nightmare. And the last tip from my side here is that if you want to save time by not calculating all these 57 combinations, which contain for sure some combinations that are duplicates or not dangerous, we have this algorithm we call calculate load extremes. If I push that, it automatically detects the duplicate load combinations or the load combinations that don't contain any extreme of any internal force on any member. If you'd like to learn more about this algorithm, just go to our webpage, ideastatiCa.com, and search for this key word or key phrase. You will find an article explaining what's behind it. All right, the last step now is to calculate the connection. In order to save time on this webinar, the calculation would take about 2-3 minutes. I have pre-calculated the connection, so I'll show you just quickly about the results. We can see this connection is well designed. Mostly it's green yellow. That means the utilization of those components is under 100%. That means we passed the code checks. I can see the equivalent stress. For example, I can go through the detailed checks of any bolt. For example, I go back to this overall display and I click on this bolt, you can see the bolt overall results in this row and also the detailed results and the formulas from the code. This time it's pseudocode. with field numbers in here. So everything is crystal clear. Last step, what I would do is go to report and generate the report with any settings that I would like to have here. Push that, and then I can save it in PDF or open format in doc for further editing. What is my very last tip is that you can export your connection to IFC format and then load it into your, for example, TECLA or another CAD software and have it as a IFC reference there and work with it further on. All right, so that's it from my demo. From my side, I will jump back to presentation and we will continue with the last part, and that is how to avoid all that I have just shown you using the BIM links and save all these about 30 minutes of modeling by simply pushing an import button. Before that, I will ask Duncan to run the second poll of this webinar. Are you ready, Duncan?
Oh, I was born ready, which was quite alarming for the hospital. Okay, so we have a quick poll here about how regularly you use IDEA StatiCa BIM links. I'd like to say very useful connection application tips from your pocket there, Adam. You must have extremely large trousers.
I do.
Yeah, he's the only person I know who can do the twist undetected because these trousers are so huge. Okay, so we have some answers coming in. Perfect. So 58, oh, the numbers are going up.
I see. In the meantime, I'm twisting here.
He is, ladies and gentlemen.
Hoping for more answers to come out in this poll. But I see the most of our attendees has voted, so we can close this poll and show it.
Okay, so let's see the poll results there.
Mm-hmm.
Surprises there, Adam?
Not really. I see that a lot of our visitors today don't use BIM links at all. We can wonder why, but that's actually a good thing that we will show you now, or Ondra will show you now how to do that. So the next webinar where we will run this poll, we await to have 0% in the last vote, right?
Perfect.
So let's hide the results of this poll, and I will give a word to Ondra to guide you through the last part of this webinar.
Thank you, Adam. So Adam just showed you how to model a connection from scratch in the IDEA Connection application. And now I'd like to show you how to avoid this, or at least how you can make your work easier and faster. Usually we check the connection design when we already have the entire structure in some global model. So we would like to use the data from this global model as the basis for the connection model in IDEA. And BIM links make this possible. BIM links work with FEA software for structural analysis, such as SAP 2000 or Robot, and also with CAD systems such as TECLA or Revit. And I will now briefly demonstrate both of these options. Unfortunately, we don't have the global model of the Twisted Museum at our disposal, so I will use another structure for the demonstration. Here you can see the model in TECLA, and we will focus on this joint. I have also a model for structure analysis in SAP 2000. It is already calculated, so all I need to do now is to run the BIMlink. The BIMlink is a plugin here in SAP, and when I run it, the Checkbot application will open. The Checkbot is an application for management of the imported connections or members. At first, we need to create a new Checkbot project. It will be located at the same folder as the global model. So I click Create, and the new Checkbot project is now blank, as we need to select which part of the structure we want imported. I will select only this one connection, but I could import the whole structure and then work with all connections in the Checkbot model. Now I can open the selected connection. It's the only one in our case, and you will see that the geometry of the beams, the material, the cross sections, and the load effects all have been imported, and we can use them as the basis for further work with the connection. So here you can see how it looks, and now I could go on the same way as Adam, but in our case, as I showed you, we already have modeled all the welds and bolts and plates in Tekla, so we want to use this model and not to model it again in IDEA StatiCa. So once again, I run the Checkbot plugin, this time from Tekla, and I will repeat a similar procedure. A new Checkbot project will be created, this time from Tekla, and I need to select what to import once again. This time I need to select the node, then the connected beams, and finally all the elements I want to import. With these inputs done, the import will take place, and as you can see here in Checkbot, the project looks very similar to the one created from SAP, but now you will notice the big difference when I open the connection, because here the situation is opposite. You can see that we have all the operations present here in the model, but what's missing is the information about loads. So the last thing I want to show you is how to merge these two connection models we created, and for that I will use this button, connection import, and now I need to find the connection created in SAP. Double click it, and you can see the loads were successfully imported. Now all we need to do is to run the calculation, and we didn't have to model anything inside the IDEA application. So with this, I would like to end the demonstration, and I will pass the word back to Duncan.
Thank you very much. Let me just grab that beautiful screen. There we go. So it's question and answer time. So we have some questions have come in. I will throw them over to our resident experts over here. So the first question I have is, okay, the questions are so good I can't. Yes, can the weld grade be set to automatic by default so there is no need to change each weld grade manually?
All right, that's probably a question for me. And I will answer that. For that, I will just take the presenter for a minute to show you where you can do that. So, show my screen. I'll demonstrate it on the model. So the question is, if I add any weld in the program, how do I make sure that it always uses the default material? So this is actually automatical. So automatically, any weld you add, it uses the default weld material, and you can change the default material of welds in the project settings in here. Okay, so by this I can change the default material for all welds. Also, what you can do is, if I multi-select, for example, all those cuts here, I can also, I'm sorry, I'll go to these operations. Here I can also change and add different material of welds for all operations in my list. So there are multiple ways how to define that. Okay, enough. Presenter, back to Duncan.
Okay, perfect. Beautifully answered. So let me show that screen again. So the next question, I believe, Andre, you're going to answer this one. You don't know, but you are. How would you align the list of members imported from CAD model and internal forces from FIA imported connection model?
Okay, this is something which is done automatically. The user doesn't have to align anything because the vectors of members are compared during the import and they are matched, so nothing needs to be set by the user there.
Perfect. Okay, great. Where would we be in the webinar without an additional poll? So we're going to do our final poll of today. So let me just share that with you. I'm expecting very nice answers to this one. So, question, what kind of webinars do you like? Maybe, Adam, I can ask you that question. What kind of webinars do you like? Apart from ones with you in. Okay, before you answer, very wise. Great, yeah, good answer. And I think that the Twist project is a fantastic example of that. So I think we have, oh, people are still voting. We'll give you another 10 seconds to get those votes in before we have a look at the final results. Okay, so you had your chance. Let's have a look. So we can see the results there. So the winner is Modeling of Connections, Learning Tips and Tricks. Well, certainly you've learned a lot here today, which is why you're here. Excellent. So let's go back to the presentation. Okay, what's next? Okay, so we have some webinars coming up. Join us on March the 19th, where you can learn about how to design and co-check complex anchoring details. And then in April, the date is not yet chosen, but there'll be another Still Connections webinar filled again with the amazing tips and tricks that can really save you a lot of time and learn especially by example. Also like to remind you that for your kind of self-paced online training, there is IDEA StatiCa Campus, and we're very pleased to announce that we have just launched the Basics and IDEA Parametric Design, proving that for everybody, parametric design is now an option. It is a very nicely paced and practical course, and I think you'll find that parametric design is one of the ways of kind of future-proofing your work. So there's a lot of value in that. Okay. As we are closing the webinar, you will receive it. There'll be a short survey after this webinar ends. Please do complete it. For those of you who would like to watch it again, the recording will be available in the support center and also on our YouTube channel. I believe you'll also get a recording through email. You will indeed. Everyone's nodding to confirm. And for those of you who haven't taken out a trial version yet, we really urge you to do so, where you can practice what we've preached today and try out some of the amazing time and savings that you will achieve when you start implementing IDEA StatiCa into your workflow. And of course, we have the gloriously full and useful support and learning materials in our support and learning center. So do ensure that you make use of those and you'll find probably most of the answers to your questions there, and probably even some answers you didn't know you needed to know. So all that remains for us is to say goodbye. Thank you very much for attending. Should we switch on the webcams and wave to everybody? Let's do that.
Here we are.
Yes, Andre's a bit shy there. Come on, Andre. There we go. Okay, so thanks so much for joining us for today's webinar, and be sure to join us for the next one. So I wish you all a fantastic day, and thank you once again, and goodbye.
And thank you from my side as well. Have a beautiful rest of the week.
Thank you all, and goodbye.
Bye.